Good afternoon. My name is Jonas Envall and I work with product management and business development focused on UAS at Carmenta. Today I will talk about visualizing and analyzing geospatial information for UAS, and I will look into two use cases in more detail: safe landing zones and nap of the earth flight. The first question we can ask is, what is required to successfully plan and manage a UAS mission? Well, above all, in my opinion, is that you need an up-to-date operational picture. This is achieved by combining and visualizing in real time different types of geospatial information, sensor data, and dynamic events. This can be tactical overlay, airspace information, or really dynamic data like live feeds from radar systems or video streams from drones. But it's not all about visualizing. It's equally important to be able to analyze this information to help the user make sense on what is going on in the map and get a full situational awareness. This picture is an example of this. As you can see, the 3D map is built up of several data sources. At the back, we have a low-resolution orthophoto that has been combined with an elevation model. One step closer to the camera, we're using a 2D data source that contains building footprints with height information to extrude boxes that represent the buildings. Finally, closest to the camera, we have a really nice 2 centimeter high resolution city model that we got from our friends at IGI. We're using this 3D environment to perform analysis, as you can see. We have generated a route for the drone that goes through the city, avoiding buildings and trees. You can also see the parts in blue that represent the so-called view shed. That is what can be seen from the current position of the drone. For example, you see the small spires here on the church that leaves shadows on the roof. Finally, you can also see a vertical profile below that shows the route displayed on the ground below. This is one example of how analysis functionality can help the user figure on what is going on in the map to get a better situational awareness. Let us now take a brief look at 3 examples of geospatial analysis functions that are relevant to the drone use case. The first example shows airspace coverage. Here we use the same higher resolution 3D model from Münster that we saw before. In the picture you see 2 observers, one in the middle and one a bit more to the right. Here and down here. The red volumes surrounding here indicates the parts of the analyzed airspace that cannot be seen by either of these 2 observers. This allows the operator to optimize sensor position and identify and analyze blind spots and strategically place sensors to achieve good coverage. But understanding airspace coverage can be very complex. To give the operator a clear picture of how good the airspace coverage is, we can therefore calculate and visualize the airspace coverage in real time in an easy to understand way. We can also show the volumetric line of sight, that is what is seen by one particular sensor. In the second example that I'm going to show, we show a video stream from a drone projected onto a 3D map. Here you see the drone on top, you see its trajectory here, and you see what part of the map the camera can see. You also see the actual image coming from the drone camera projected on top of the 3D map below. Overlaying a live video stream from my UAV onto a map significantly increases the usability of the video, as everything that happens in the video is geo-referenced immediately, and you can all at once get an understanding of exactly where it is. The third example we're going to show shows vertical clearance. By using vertical clearance along the flight path, potential obstacles and hazards can be identified and avoided. Here, for example, you see the red indicated areas here. These indicate that in this part of the flight corridor we have a too low threshold towards the safety margin. And you can also see the red line here that cuts through the terrain. Let us now take a closer look on how we can use geospatial analysis in a use case that is an essential part of many UAS missions, that is determining safe landing zones. There are different occasions when a safe landing zone may be needed. One occasion is when making deliveries at a specific destination, for example, when delivering supplies to military ops or when doing an emergency medical delivery. But it can also be part of a last mile delivery for both defense and civil use cases. It can also be important to be able to identify safe landing zones along the route in case of an emergency during a flight. Here we need to ensure that a safe landing zone can always be reached, and that the drone can be recovered in case of an emergency. And if we don't find a safe landing zone within the desired distance around the route, then we might need to adjust the route. So what is a safe landing zone then? Well, to be considered as a candidate for this, an area must meet certain conditions. It needs to be safely away from hazardous obstructions. It needs to be suitable based on terrain and land classification. It needs to be reachable with reduced capacity. And also it needs to be reachable from a road network, so it's easy to recover it. We don't want the drone to land on a mountain, for example, where it's really hard to get to. So how do we go ahead and calculate the areas that can be good candidates for landing zones? Well, we start by looking at the elevation data. Areas where we have a large change in elevation, that is, slopes greater than a certain value, are not suitable for landing with normal drones. Instead, we try to find sufficiently large areas with sufficiently flat ground. A degree of a slope can be computed by processing terrain elevation data. Next, we take the classification of the terrain into account, where we're looking for good landing spots. In this picture, dense forest is dark green, urban areas are pictured as red, water is blue, and open grass fields are light green. In our example, only the open grass fields are determined as suitable for landing. In a real world scenario, we would of course have many more terrain types, and different of them would also be suitable for landing. We also add a buffer around these areas to get an extra safety margin away from dangerous terrain types. Once the constraints are combined, it is possible to easily identify good land locations for landing along the planned route. Identifying candidates for landing spots help the UAV to fly directly to a potentially good landing spot. And finally, the UAV can then use its onboard sensors, for example its LiDAR or proximity sensors, to make sure that no cars, boulders or other hazards are in the way and a safe landing can be performed. Of course, we might not have all these more dynamic things in our data feed. But if we do have, then of course this can be also put into the analysis. Next, let me go into the other analysis that we'll look at in more depth, the route calculation for drones, and more specifically, nap of the Earth flight. Here we want to calculate the best route for a drone mission. But what does best route mean? Is it the safest? And in that case, what does safe mean? Is it the shortest? Is it the quickest? Is it perhaps the most fuel efficient? Is it the most hidden? Is it in range of the instructor? Is it outside certain zones? In most cases, it will be a combination of a multiple optimization goal depending on the operational needs. In our example, we will focus on two optimization goals, speed and safety. Balancing speed and safety is an example of a multi-object optimization, which is complicated. Even if each of the objectives can be described as a number that must be minimized or maximized, there is no definite way to compare numbers of different kinds. Think of these objectives as different currencies that do not have any official exchange rate. This makes it hard to rank the solution. Travel time is an objective that's easy to define, but safety is harder. Ultimately, of course, we are concerned about the probability of mission success, but it would be hard to calculate and combine risks in terms of probabilities. Instead, we use a different approach for simplicity, where we explicitly define local risks in various zones. The risk in each zone is represented by a safety factor that sets an exchange rate between speed and safety. This simplifies the routing problem since we can now optimize for a single objective instead of several. There are many different ways that a drone can be hidden. One basic assumption that we have here is that the aircraft is safer when it flies low and is concealed by terrain to a certain degree. Other ways could be flying really high to be above the clouds, or just so distant so you can't be observed. But looking at these low-level flight, there are different kinds. There is the normal low-level flight that goes straight above the terrain. There is the contour flight that follows the terrain but in a straight line, just changing the altitude. Finally, we have the nap of the Earth flight that deviates from the straight line to follow the terrain as much as possible by avoiding obstacles like forest and hills, and follows valleys that may remain hidden. Let us now look at an example of a nap of Earth route that we have generated. Here we have a route that starts at a certain waypoint, down here, and then visit 3 other waypoints on its way. Let's assume that these waypoints are places where the UAV needs to be to make an observation. But between these waypoints we would like to travel as fast and safe as possible. Since aircraft flies slower than when it has to climb or descend in our model, we can also see that the high ridge here is the fastest route for the middle leg, given the nap of the Earth flight is mandatory between the waypoints. But this is obviously not an ideal way to fly if you want to remain fully concealed. So let me at this point introduce another concept that we'll use, the visibility index. The visibility index for an observer, the eye in this example, says how much of the surrounding terrain as a percentage of the target circle can be seen. Here 63.4%. Within the observation area we can also display the visibility indices for all possible positions as isolines, with a transparent color ramp. So for example, here you have a 60% visibility of the area around. Here you have a 20% visibility of the surrounding area. A position with a low visibility index is concealed, since line of sight can be used in both directions. If our aircraft cannot see much of the ground terrain around it, there are also few places from which a ground-based unit can see our aircraft. Now let us use the visibility index to adjust the route to prefer concealed areas, displayed as green areas in the image here. Here we can see that it's now better to fly near but below the ridge than in the center valley line or at the ridge. Let us instead assume that we know that a threat is somewhere northeast of our route. Well, then we no longer need to use an omnidirectional visibility index. Instead, we can calculate for a certain bearing. Here we get by directional concealment areas where slopes are facing southwest are most concealed, and the route will go into the safer side of the central ridge. So we have a threat coming from up here, and we travel just below the ridge on the other side. Let us now introduce a new element called risky airspace, represented as yellow volumes. These indicate risky or softly restricted airspace, for example residential areas. These are possible to pass through, but we rather fly somewhere else, and flying over these areas comes with a cost in the optimization. So in this example, we do have a route and it prefers to pass through this yellow area at its most narrow place, but it would be more expensive to go around it. Finally, we have airspace that is totally forbidden, and this is displayed as red volumes of different shapes. They can, for example, represent restriction areas, closed airspace, or enemy threats. Observe that the route can still pass under the area on the left here, due to the concealing ridge that makes the line of sight from this observer hidden by that ridge. And it's also possible to pass over the restriction area on the right, since it's just restricted up to a certain altitude. In this image, we put it all together. The UAV starts on the big field on the left, where you can see it. The yellow zones represent residential areas where it's not forbidden to fly, but we would like to avoid flying too much in it. Finally, the red zones represent high security areas, like sensitive factories, where flying over is not allowed. We also have a suspected threat in the bottom right corner that we want to avoid. So if you follow the route here, it goes, starting from this field, follows the edge of this yellow area, goes through it in the most narrow place, goes beside the next yellow area, passes through it in the narrow part, goes over this field, passes through yellow, avoiding the red, and goes up using nap of the earth flight up in the mountains. That was everything I wanted to present today. Thank you for listening. If you have any question or want to learn more about this, don't hesitate to reach me at the address given below here. Thank you very much and have a great day.